Hey my dear warriors, welcome to the electrostatic sessions, guaranteed 12 marks in your NEET 2023 or 2024 exam. It's a very important chapter because 12 marks is not worth losing. It can decide whether you're going to get a government college or not, right? So in today's session, I'm going to do concepts, problems from the chapter of electrostatics and Gauss's law. So all those concepts, right from force, the Coulomb's law, field, potential energy, potential difference, the relationship between field and potential, dielectrics, and then you are going to see dipoles, then electric flux, Gauss law, applications, and the fields and potentials for different geometries, including the properties of field and potential lines, as well as the properties of conductors. So all of this in today's session with me, Shreyas, your physics master teacher. And shower some love quickly in the chat box by, first of all, going below the video, smashing the like button, and if you are not yet subscribed to the channel, make sure you are subscribed. Hi Shaku, Vignesh, hello Hariharan. Yes, this is enough for getting good marks, Hariharan, and you have to continue watching all the classes. Hello Pooja, hello Sampath, hello Sukesh, Anusha, nice to see you guys. Hello Asing. Will I teach gravitation? Yes, when I start the 11th portion. Good evening, Vignesh. Hi, Devikas. Hello, Nishant. Nice to see you guys. So let's begin. And yes, remember the entire PDF will be available in the Telegram channel. Where do you find it? It's there down in the description box. There is a link. Join Telegram channel. Just click on that and you will be redirected to the Telegram channel where you will be able to download the PDF. So before we begin, I have a simple question for all of you. Although I'm not going to reveal the answer quickly, I'm going to probably show you a lot of theory and all those concepts. Once we do it, then you will be able to answer this question within seconds. But still, give it a try. If Pandu is positively charged and he shakes hands with Champa, who is neutral. Now Champa comes close to Baban, who is also neutral. Assuming all as conductors, then Champa and Baban, do you think they will attract each other? Or do you think they will repel each other? Or do you think nothing will happen? Or do you think the information is insufficient? Yes, this is for NEET obviously. For CBSE also you can use this definitely. So that's the reason why I planned this session, because it's a 12th standard topic. It will be helpful for your boards obviously for revising the concepts, and it is particularly more useful for NEET aspirants. Okay, many of you saying attract, some of you saying nothing, some of you saying yes, attract, and again nothing again. So between A and C, we are going to see what the correct answer should be after some time. So you need to watch the lecture completely so that you understand exactly what happens when you transfer charges, what are the different properties of conductor, when do they attract, when do they repel. Now, talking about charges have certain properties, and you might have always felt charge when you rub some rubber or plastic object on your hair or a woolen cloth or a silk cloth. When you take some objects and rub against each other, you see that suddenly your hair starts to stand, or your skin gets attracted to it, or some two objects just stick or even repel each other. So this happens because of electric charges. These are basically small teeny meeny things which have values like plus or minus, and just like masses are there, similarly charges are special, I can say intrinsic characteristic of matter. So there are three kinds of charges actually: plus, minus, and no charge, that is neutral. So you will see that the positive charges arise because of protons. Positive charges arise because of whom, guys? So I'll write it over here. Positive is because of protons, whereas the negative charges is because of the electrons. Remember, charges are scalar quantity. That's the reason why you will see charges can be simply added or subtracted. For example, I'm just putting over here, the total charge will be 2 plus 3 minus 1. So 2 plus 3 is 5, 5 minus 1 is 4. So 4 Coulomb. So the charges are basically scalar quantities, so there is no directional information. Although charges have sign, do not get confused that it is a vector quantity. Just because something has plus or minus does not mean it has direction. So it has no direction, it is a scalar quantity, you can just add them. Remember, the unit of charges is basically Coulomb. right? So the unit of charge is basically a coulomb, and you should know that either an electron or a proton has a magnitude of charge given by 1.6 into 10 to the power minus 19 coulomb. Yes, everybody knows this fact. Every electron or proton has a magnitude 1.6 into 10 to the power minus 19 coulomb, which is extremely small. Join in, Raj. Excellent. Good evening, Jernia. Oh yes. Next important thing is charges are always conserved. So if you rub something, or if the charges go from one object to the other object, charges get exchanged, or they might move from one point to the other, but the total charge in a system remains conserved. So if you take a system with boundaries, that means a closed system, they can exchange with each other, but the total charge will remain the same. Makes sense? If electrons go from here to here, the negative charge just goes from this point to other point. So total negative charge will remain the same. So understand, charges cannot be created nor they can be destroyed. The total charge in an isolated system is always going to be conserved. Everyone with me? Last one is quantization of charge. What is quantization? See, you have 1 rupee coins. These days you do not get 50 paise and all. So let's just ignore 50 paises or paises in general. So you have 1 rupee coins, you might have 5 rupee coins, you have 10 rupee notes, you have 25 rupee notes. So if I ask you to give me 237 rupees, you can easily give me 237 rupees. Because you can give me 200 rupee note, then you can give me 20 rupee note, then 10 rupee note, then 7 rupees coins you can give me. Similarly, if I ask you to give me 13 rupees, you can give me. But if I ask you to give me 12.26 rupees, you'll be like, sorry boss, I can't give. Because the smallest multiple that I can give you is 1 rupee. Same way, charges also have a multiple in which they are always present. That is always in the multiple of E, which is 1.6 10 to the power minus 19. So charges can be always 1 into this, 2 into this, 3 into this, 4 into this, basically integer times of the most fundamental charge, which is basically your E, which is 1.6 into 10 to the power minus 19. Okay, I hope this is clear. Obviously, sun has charge, earth has charge, you have charge, everything around you has charges. Everything is made of charges. Just that some things do not reveal themselves so easily, because the amount of positiveness is the amount of negativeness. So they nullify and they behave as a neutral body. But remember, it could be made of equal amounts of positive as well as negative charges, because that's what atoms are, Susanta. Hai na? So moving ahead to the next point, and a question coming up on your screen. If a body has minus 80 microcoulomb of charge, the number of additional electrons in it will be how much? Just imagine, if a body has minus 80 microcoulombs of charge, then how much the amount of charges do you think are there in it? Think about it. We all know that the total charge is the number of charges into E. Therefore, the number of charges will be the total charge divided by E. So the total charge, I think it is given 80 microcoulomb. Micro is 10 to the power minus 6. And E value, I might be like, sir, why are you not putting minus sign? See, I'm only interested in the magnitudes. I know it is going to be electrons only. So I'm counting the number of electrons itself. Each electron has a charge of 1.6 into 10 to the power minus 90. So if you want, you can write this as 80 divided by 16, and you will have 10 to the power minus 6. This can be written down as 10 to the power minus 20. Bring it on the top, it will become 10 to the power plus 20. We know this is just going to be 5, and this is going to be 10 to the power 14. That's the answer, guys. That's the answer, option C for Captain Shreyas. Hello, Prem. Is that understood? This is how you calculate how much charge is present in any body. I have just used the concept of quantization of charge. Quantization means everything is in a multiple of a most elementary thing. Charges are conserved. They are intrinsic properties. There can be of 3 types: positive, negative, neutral. We should know the value of E. And charges are scalar. That means you can just add them. Moving on to the next concept, and that is basically your Coulomb's law. Yes, Anusha, this is live, bacha. Okay, so Coulomb's law is just like gravitational law. What does gravitational law tell you? 2 masses are there. How much is the force of attraction? Now, if 2 charges are there, how much is attraction or repulsion is given by Coulomb's law. It looks very much similar to your gravitational law. There's a small difference, I'll come to that. But before going there, remember, always like charges will repel each other. We all know this. Like charges will always repel each other, whereas opposite charges will always, what do? They will attract each other. Positive, negative will attract, right? They say na, opposites attract, similar kind of people repel each other. So I don't know how much that is true with regards to people. Everybody might have their own opinion. So this is how it behaves. Now, if I take a charge Q1, charge Q2, 5 coulomb, 2 coulomb, minus 10 coulomb, 20 coulomb, whatever charges you want to take. How much is the magnitude of the force is given by a constant into Q1, Q2 by R square. Q1, Q2 are the charges. What is R, my dear students? What is R, my dear students? It is nothing but the distance of separation. Distance of separation between the charges. Distance of separation between the charges. You can see this is the distance. Now what is this 1 by 4 pi epsilon naught? That is basically a constant. Let me just put it over here. So this 1 by 4 pi epsilon naught is roughly 9 into 10 to the power 9 SI units. So you can use that as a constant. This epsilon naught is also called as the permittivity of vacuum, or just you can call it even free space when there is nothing around. Now this is one major difference between gravitational law and electrostatic law or Coulomb's law, that if there is some medium surrounding them, let's say water, ceramic, wood, paper, then the permittivity changes of the medium. So epsilon will change in value. So the force will also change. But in gravity, there is nothing like that, okay? So gravitational force between two masses, you do not have such a thing. You just have a constant G, number one. Another major difference between gravitational law and Coulomb's law is that you will see gravitational law is only attractive in nature. Two masses always attract, they never repel. But Coulomb's law, it can be repulsive or it can be attractive. Yep, I hope this is very, very clear. Now, there is also a vector form of this equation, but you will not need that vector form for any of the NEET problems. Okay, unless they ask you, give me the formula. That would be stupidity. But whenever you have to solve problems, you know that forces are vectors. You will use basic laws of vector addition rather than writing I, J, K hat of every force and then adding them using components. That would be a very lengthy process. But still, if you like to have the vector form, guys, let me give that as well to all of you. So the vector form of the same equation, the force vector, will be given by same thing, 1 by 4 pi epsilon naught. Here you have Q1, here you have Q2, and you have R square. Here you can put basically R hat. So this is magnitude, this is the direction. R hat is the position vector, so this is the magnitude vector. So this is basically the vector equation. Usually people do not like this, it's not so relevant or not so important. This is what you're going to use. Remember, this position vector that you have over here, this can be also written down as R vector divided by R. So if you write this as R vector, unit vector is vector divided by the magnitude, then this R into R square will become R cube. So that's a simpler way of writing it. That's how you can write it down. Is that okay, bacha log? So this is vector form, this is Coulomb's law, and you can see as the distance increases, as R increases, as you take them away, the magnitude of the force will also go down. So as you take them far away, they will attract or repel weakly. When you bring them closer, the force will be much stronger. Okay, so that's the beauty of this. Now, force is a vector quantity. Hello, Santima Ji. Yes. How many hours? This session will be close to 2 hours, Pooja. Okay. So force is a vector quantity. So imagine there is a charge here, another charge here, another charge there. Each of these charges might attract another charge. Each charge will attract that other charge. So the total force will be the vector addition of all these forces. Look at this charge. Bichara. This friend is also calling. This friend is also calling. This friend is also calling. This friend applied F3 force. This friend applied F2 force. This friend applied F1 force. It could be attraction. It could be repulsion. All these forces together. How do you add forces? Triangle law, polygon law, vector resolution, IJK components, whatever you want to use. You want to use the formula, whichever technique you want to use, whatever you have studied in the 11th grade. That's it. Use those and you can find the net force acting on that charged particle. This is basically called as the principle of superposition, meaning superimposing each effect. This guy will also apply force. This guy won't say, oh my god, this friend is there, I will not apply force, Baba, what will he think? No, they will be like, I am going to apply the force. This guy will not think, oh, this guy is there, this guy is looking, should I apply my force F2 or not? Nah, they don't care. Whether they are there or not there, they will apply the force. So independent of the other charges, they apply their forces. That's why the total force is the vector sum of all these forces. Is that okay? I hope this is clear. Yep. So yes, nuclear forces are spin dependent forces, like I have told you in the nuclear physics chapter, and they completely depend on which direction and how they are spinning and all that. So there is a big theory. If you do take up nuclear sciences, you will learn more about it. Okay. Moving on to some questions coming up on your screen. Two charges of equal magnitudes and at a distance of r exert a force of F. If the charges are made half, distance between them doubled, then the new force will be how much? Hello Santosh. Hello Santar. Come on, figure this out. So let's understand the question. There are two charges. There are two charges of equal magnitudes. That means if this is Q, this is also Q. The distance between them is R. Then the force between them will be basically some constant, that is 1 by 4 pi epsilon naught into Q divided by basically R square. Basically it will be KQ square divided by R square. That will be the force. Now in the second scenario, what has happened is that the charges are halved. That means this is Q by 2 and this is Q by 2. The distance is doubled. So this is basically 2R. Now think what will happen. The new force will be K, and then you will have Q by 2 into Q by 2, and then you will have 2R's whole square. So this will become KQ square by R square. 1 by 2 into 1 by 2 is 1 by 4. 2 square is just 4. So now this number over here is just this value of force. This number over here is basically just this force. So might as well just write it as F only. And 4 into 4 is basically 16. So this is basically your new force. So the new force is 16 times less, or 1/16th of the original force, which is option D. Exactly, Prem. Yep. And so many of you. Pooja. Yes. Nandini. Very good, Sampath. Awesome, Hariharan. Excellent, Sai Baba. Very good. Very good, Saran. Awesome. 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 Great. So these kind of questions do come very frequently in the NEET examination. So just a matter of calculation. Let's do one more kind of question which can probably come in the NEET exam. And here it is. Three charges are there. 1 micro, -1 micro and 2 micro. They are put in air. Okay, so vacuum like thing. ABC, equilateral triangle vertices. Side length is also given. What is the net force at point C? Interesting. I think vector addition will be involved. So might as well draw a triangle over here. That will benefit us. Okay, and let me also label them. This is A, this is B, and let's say this is C. So what are the charges? Let me write it down. 1 microcoulomb. So 1 microcoulomb. Then you have -1 microcoulomb, -1 microcoulomb, and then you have 2 microcoulomb over here. The question is, what is the resultant force? Okay, but before that, this side length is 0.1 meter. It's an equilateral triangle. What is the resultant force on charge C? Interesting. On C, this guy as well as this guy both will apply force. Which principle is that? Superposition, vector addition. That's all. So 1 microcoulomb will apply a repulsive force because they are equal in sign. Plus and plus will repel. So definitely along this line, I should expect a repulsive force between these two. correct? Similarly, between this guy and this guy, because they are opposite in charge, sign, that means they should attract each other. Interesting. Now you guys only think and tell me whether the length of these two vectors will be same or different. Will the magnitude of this force and this force be same or will it be different? Just put it up in the chat box. What do you guys say? Because that plays an important role on how you're going to solve the problem ahead. Think 1 and 2. 1 and 2. Oh, the product of the charges is same magnitude wise. Okay. Distance 0.1 meter, 0.1 meter. Obviously, it's an equilateral triangle. This is also going to be 0.1 meter. Distance is same. Product of the charges is same. Magnitude wise, obviously they will be same. Perfect. So if I label this force as F1, obviously this will be also F1. If this is F1, this is F1. If this is F1, that is also F1, magnitude wise. Now that will help me that, the calculations might be probably a little bit easier. Okay, how do I add them vectorially? There are many ways. You can use triangle law, this law, that law. But I feel I can just use my simple logic that if I want to find the net force, the formula that I know from vectors is this. It is root of F1 square or A square plus B square plus 2AB cos theta. So A square plus B square plus 2AB cos theta. Oh, what's this angle? What's this angle? I know that internal angle, the inside angle, because it's an equilateral triangle, it is 60 degree. So obviously that outside angle has to be 120 degree. So this will be cos of 120 degree. This will be cos of 120 degree. The whole angle between this yellow force and that yellow force, this entire angle that you have over here. Make sense? Okay. So what does this become? So this will become basically F1 square common 1 plus 1 plus 2 into cos 120, guys. What is it going to be? Minus half, because cos is negative over there. So what is it going to be, guys? It's going to be root of F1 square. 1 and 1 will cancel and just you will have 1 plus 0 basically. So that's just going to be F1. And what is F1? It is nothing but K Q1 Q2 divided by R square. Use that formula. So 9 into 10 to the power 9. Charge 1 is 1 microcoulomb. Charge 2 is 2 into 10 to the power minus 6. So that's coulomb. And divided by distance. Distance is basically 0.1. So whole square. So why is this minus 6 coming power? Because it is a microcoulomb charge. Now do the math. You are going to get it. Shaku, they are same because distance is same. Look at this. Q1 into Q2, same, right? And distance is also same. So obviously force will also be the same. Understood? Charge at B is 1 and charge at C is 2. Exactly, that's the whole point. 1 into 2. Charge between these two is 1 into 2. Force between these two is 1 into 2 divided by R square and that K. Force between these two will be 1 into 2 divided by R square and again that K. So the product of the charges is same. Product of the charges is same. Distance is same. Obviously the force will be same. Tamil, yes, you can do that, but you'll have to study. You have to put in a lot of effort. Don't just expect that watching lectures, you're going to score like, 700 marks. No, if watching lectures, if anybody could score 700 marks, then the teacher is lying, the institute is lying, and everybody would be a topper. Remember that. Okay, cool. So the answer comes out to be 1.8 Newton when you solve this. So answer comes out to be 1.8 Newton. Exactly, Sampath. Ashrita, very good, very good. Hariharan, Sauntar, Nishant, so many of you have answered it. Very good, Shaku. Looks like you understood it. Yep, great. So that was the critical point why the forces are same. The forces are same because it is some constant into basically charge 1 into charge 2 divided by the distance square. So that's why the forces were same. That's why both were F1 and F1. That's it. So that's the logic behind it. Moving on to the next concept, and that is basically how do you charge? There are two ways of charge. One way is conduction, second way is basically induction. When you say that I want to charge this thing, I want to charge that thing, I want to discharge something. So one way is you conduct the charges. The second way is you induce the charges. So what are these two ways of basically charging? Let's have a look at it. See, if I have a charged body and then let's say I have an uncharged body, okay, neutral. Now I touch these two bodies. So maybe this body had some charge like this. The positive charges jump onto the other charge or on the other body like this. So they jump. Maybe these positive charges go here. Some other positive charges remain. This process where physical contact is involved, some path is there, that is basically called as conduction. This is basically called as conduction. You can see that there is a conducting path. There is a conducting path involved, and you will see that the charges actually get transferred. The charges actually get transferred from one body to the other body. That is conduction. Like I take a charged metallic sphere and I touch it to another metal, I'll see the charges will flow. Or you might have experienced this. Sometimes you rub yourself on the woolen blanket or something and you go touch a doorknob, suddenly you get a shock because there is electricity conducting via your body from your fingertips to the doorknob, and that's why you get that slight shock, you might think. Yeah? So that's what happens in conduction. Whereas in induction, charges are induced, you do not need physical contact. Something like this, observe now. Imagine I take a positively charged body or negative charge, does not matter. Now there is some neutral body very, very far away. Right now they are very, very far away. That means they cannot influence each other. But when you bring them close by, then what you will see, they are not touching, but this positive charge will attract the electrons in this body. Okay, the electrons will come over here, and an equal amount of positive charge will be developed on the other side. So these charges over here, they are called as induced charges. Why these charges have come? Because the positive will pull the electrons from this body towards this side. So these electrons have left these positive charges on their way back. So these positive charges got exposed and the electrons have migrated to the other side. So the electrons are the ones which actually travel. Notice. So there is migration happening within the body. So these charges are called as induced charges. Everyone with me? I hope this is clear. Okay, both these methods are very, very important. Moving on to some questions now, coming up on your screen. There is a metallic sphere A given positive charge, another sphere B given, whereas another identical metallic sphere B of exactly same mass as of A is given an equal amount of negative charge. Then which of the following is true? I think the word mass is missing. So let me tell you that this word over here is actually mass. Same mass of A is given an equal amount of negative charge, then whose mass is more, whose mass is less? Come on, think about it. Let's take both the cases. Metallic sphere A is given a positive charge. Okay, so this is metallic sphere A and that is positively charged. Then we have another metallic sphere of the identical as that of A. Okay, and then it has the same mass, but it is now given a negative charge. So when you actually charge it, do you think their masses will still remain the same or will it be different? Oh, is it? Nuclear physics was not done. I think it should be done, bacha. I'll have to check. Let me check, bacha. I think I've done it. If not done, then I will do it. Yes. So the one with electron, exactly guys. Yep, mass of B will decrease and that of sorry, I think it should be the exactly opposite way. Yeah, so it is going to be mass of A will increase or mass of A will decrease, actually it should be. Okay, so I'll tell you what exactly will happen. A is given positive charge. If A is given positive charge, that means you have taken out electrons. Electrons are taken out. That means the mass will reduce. The mass will reduce. That's why the positive charge has come. If B has got negative charges in it, B has got negative charges, that means electrons are added onto it. That means the mass should actually increase. Mass should actually increase. So option B is correct. Mass of B increases, mass of B decreases, obviously wrong. Mass of A decreases, mass of A and B remains same, obviously wrong, guys. So it is actually option D. Yep. Electron has negligible mass. Exactly, Shaku. But that's the whole point of the question. Why do you think they ask the question? Because they want to see whether you understand what is the meaning of positively charged body or negatively charged body. Do you understand that negatively charged body has small amount of extra mass because of the electrons? I know it is negligible. You won't see it on the weighing scale, but it is there. And do you realize that is what they are going to test? You should see all these things. You should understand what the examiner is trying to ask or wants from you. He wants to test whether you understand electrons leave the body or enter the body. That's what he wants to see. Otherwise, mass wise, if I have to write, if this is 27 kg, this will be also 27 kg. Okay? Hardly the difference will be in some decimal somewhere after some 20 or 30 decimals. But that difference is what is important. Okay. Next, Pandu is positively charged. Interesting. I'm similar to Messi in football. I'm so glad, Naveen. I should be the Messi for physics. Messiah. I hope someday. If Pandu is positively charged and shakes hand with Champa, wow, she's neutral. And Champa comes close to Baban, my God, some love triangle is happening. Who is also neutral, assuming everybody is conductor, then Champa and Baban will attract, repel, nothing will happen, can't decide, too confused. Come on, my dear warriors, figure this out. What should be the correct answer to this? See, Pandu, Champa and Baban. So this is Pandu, this is Champa and this is Baban. So initially what is happening, let's write it down. Pandu is positively charged, they are neutral. So basically no charge, I will put not applicable or just I'll put 0 over here. I'll just put 0 over here. Now Pandu and Champa shake hands. So what will happen? The charges will get distributed. So if there were many positive charges over here, so what will happen? Few positive charges remain here. Some positive charges go over here. Correct? So this is what is going to happen. And Baban is still out of the picture. Now what happens? Champa comes close to the Baban. Champa comes close to Baban, who is also neutral. Acha. Now Pandu is out of the picture, guys. Don't worry about Pandu. Champa just comes close to Baban. So what will happen to Baban, guys? He will get induced charges. He'll get induced charges. Here the charge got conducted. So from this step to this step, what has happened is basically conduction has happened. Conduction of charges has happened. But here induction will happen. You will see the positive will create negative charges here and positive charges over here. This polarization is basically the induced charges. The induced charges. So there will be definitely induced charges. Basically you can call it that it has been polarized. Polarized means you have separated. You have separated the fragments, separated the different ideologies. Okay, you have created polarization. Means separated oppositely charged things. They don't like each other, you are keeping them away. That's what is polarization or inducing charges in that other body. Now think logically, my dear students. Over here, isn't the negative charge closer? Isn't the negative charge closer to the positive charge? So shouldn't the attraction be actually stronger than the positive? They are far away. That means there will be repulsion. There will be repulsion. Think about it. So the attraction will be stronger than the repulsion because the negative charge quickly comes close in this Baban. So if negative charge is close, attraction is stronger. Positive charge is far away, repulsion is smaller. So there will be a net attraction. So the net force will be basically of attraction. Hence the correct answer for this particular question. This particular question's answer will be attract each other, but not because of love or anything, but because of electrostatics. Yes. Question creation of my creativity. And this is how I want you guys to think. You should always think of some mythological, mystical, imaginative, creative scenarios in your head, and that's how you should convince and understand concepts. If you go by the book definition, oh, this charges go like this is conduction, this is induction, blah, 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 blah. If you keep saying it 100 times, you will not understand it. But make some fancy examples, make funny examples, something which you're going to remember. Maybe with your friend or relative or some stupid thing or your film hero or heroine, whatever. But that's what is going to make you remember stuff, okay? So moving on to the next point, and that is electric field. Yep. So what is field? Field means, some teachers are there. If you enter the class, you automatically become silent. You will not make noise. Yes or no? Some teachers are there. You enter the class, chill, it's okay. I can talk, I can sleep, I can just do whatever I want. I'm just going to relax. Teacher is not going to catch me. Some teachers, even if they are not looking at you, even if they are not probably close by you, but they are inside the class, you will be like, Ayyo, I should keep my finger on the mouth. I should not even look here or there. I should just sit quietly. I should not make any noise. Yes or no? Happens? Very good. So, my question to you is, that strict teacher who was there, has the teacher slapped you? No. Maybe you have seen the teacher slapping somebody or something, or maybe nicely scolding or calling the parents or, doing something. So, that's why you are scared. You know the teacher is capable, but the teacher is not doing anything to you. You just have the presence of the teacher only is enough for you to be scared enough. Same way, charges need not even apply force onto somebody. Charges need not even apply force on somebody. But the mere presence of a charge is enough to create its own aura, its presence felt around it. That presence which a charge makes everything around it feel is called as the field of a charge. Is called as the field of the charge, and the field at a point is the force experienced per unit positive charge. In other words, it's force per unit charge. It's a way of testing the field. I want to know whether there is field or not. Like, okay, let me take a test charge. You take 1 coulomb. How much force are you experiencing? Okay, 100 Newton per coulomb. So your field is 100 Newton per coulomb. Okay, you take another charge and you see, it is 50 Newtons for that 1 coulomb, but it is this way. So the field is 50 Newtons per coulomb, attractive or repulsive, depending on what the charge is. So that is your field, my dear students. So electric field is basically force per unit charge. That's the reason why you will see force is field into charge. So that is the formula for force. This is the formula for field. Everybody should know this. Obviously, the unit of field is none other than Newton per coulomb. You can see Newtons on the top, coulombs at the bottom. So obviously Newton per coulomb. Also, remember one more thing, that if I have a charge here, another charge here, another charge here, and another charge here, something like that, and I'm at this point, then due to this positive charge, I might get a field like this. Let's say I call it E1. Due to this charge, maybe I get a field like this. Maybe I call it E2. Maybe due to this, I get a field like this. Maybe I call it E3. Maybe due to this charge, I get a field called as E4. All these fields are independently acting at a point. Nothing is there. If you place a test charge, then you will experience a force. But right now, what you are getting is the field. Then the total field at that point, is the vector sum of all of them. So the net electric field is simply put E1 bar plus E2 bar plus En bar, or whatever is the last charge. So vector sum. So this is again your superposition principle. This also verifies the fact that it is a vector quantity. So direction becomes very, very important. Also, notice one more thing. If you take a positive charge, then no matter where you are around it, the another charge placed close by it, which is a unit test positive charge, will always experience repulsive force. So always there is a repulsive field. So what kind of field is this? This is a repulsive electric field which is there around a positive charge. But if you take a negative charge, then what you will see is the field is attractive for a unit positive charge. If I take 1 coulomb of charge, then that negative will attract that positive 1 coulomb charge. Hence this is going to be an attractive field around that particular charge. Is that understood, guys? Okay, so that's all about field that you should know. Okay, now yes, I have put up the diagrams also, you can see the negative charge, attractive field, positive charge, repulsive field, because if you put a positive unit charge, it will push it away. If you take a same unit positive charge here, it will pull it towards it. So that's why negative charge will create attractive fields. Okay, one more thing before we go ahead. Okay, what is the value of the field? Hello Sweta. What is the value of the field at any distance because of a charge? If you are at certain distance, r from this point, then what is the value of the electric field at that particular point? That value is given by, simply put, 1 by 4 pi epsilon naught. Instead of q1, q2, right, you just put q divided by distance square. There is no second charge because you have already divided it by small q. So that second charge has vanished in that force. So that's why it's just k q by r square, or 1 by 4 pi epsilon naught q by r square. So this is the formula for field due to a point charge. This is field due to point charge. Keep this in mind. Okay. Let's solve some question. Sir, this field direction picture is due to only a positive test charge and it will change if you place a negative test charge. Yes, Shaku, very good. But let me tell you, your test charge always has to be positive. This is a universally accepted standard, because just like Shaku thought, I can take negative test charge also. Somebody else will think, I will not take a charge only, I'll take neutral charge. So everybody will come up with different theories. So they made a standard. Everybody should always use unit positive charges to define field. That's how it has been defined. So you will always test it using a positive unit test charge. Is that okay? So that's very important. It's a standard. Please understand that. So this is basically a standard for all the scientists and physicists around. Okay. Look at this question. Look at this question. In this figure, two charges, Q2 and Q3, are fixed along the y-axis and they exert a force in the positive x direction on charge Q1. Okay. So these two together exert a positive force on charge Q1 along the x-axis. Now if a positive charge Q is added at x, 0, you add a new charge. Here there were only two charges pulling or pushing this. Now there is another charge placed over there. Then the force on Q1 will still increase, will decrease, will point in negative x-axis, will increase, but the direction changes because of the intersection of Q with Q2 and Q3. Whatever you think is the right answer. Come on, I want everybody answering this. I want everybody answering this question. Come on, think about it. What should happen to the net force? Hint is, draw the vectors of the forces, you will get an idea. These two charges on this charge exert a net force along the x-axis. So the net force is over here. If the net force in the first case, F1 net, is in this direction, that means this charge will be pulling like this charge will be pulling like this, correct? So this will be force 2, this will be force 3, right? And because both are pulling towards each other, that means they will be oppositely charged. So if two positive charges are there, so my dear students, think about it. If this is positive charge and this is also positive charge, obviously Q1 must be negative because the forces are attractive in nature. Forces are attractive in nature. Now in the second case, Q1 is negative still. Q1 is, Q1 is still negative, right? Now, these Q2 and Q3 together were still pulling it this way. So this was the net force before because of 2 and 3. Because of 2 and 3. Now you have added one more positive charge. Look at that scenario. You have added one more positive charge on the right hand side. What will that charge do? Obviously that positive and this negative will also pull. There will be one extra pull towards the right hand side. So because of this, what will happen, my dear students? The net force will increase towards the right hand side. Hence the answer is option A, I believe. Yes, it is. Perfecto. Saran, Ashrita. SK, the way I can solve numerical problems but failing at these kind of questions is because it's visualization, number one. Number two, concepts. So it's not just formula and substitution, you have to think. So that analytical skills have to grow not in 1 day, 2 days, 1 week. It takes maybe a month or two to get a hang of this. So if you try now, you still have time to develop such analytical thinking. Solve riddles. Always think why. Always think how. Don't make your brain an idle object. Always let it keep working. The more it works, the more you're going to think. Moving on to the next one. Okay, great. So we have come to the properties of electric field lines. So just some time back, I showed you the electric fields of positive and negative charge. This is how a positive charge will create a repulsive field, negative charge will create an attractive field. But what if there are more than one charges? Maybe it can create a field like this. But interesting thing to note is that the field lines always originate from the positive charge and they will always terminate on the negative charge. Unless you do not have enough field lines going on to the negative charge, they might even go to infinity or come back from infinity. That's another story, but you will see positive charge can never terminate a field line. Positive charge will always originate a field line. Negative charge will always terminate a field line. It will end there on negative, start on positive. Field lines, alright, they can never intersect each other. You will never see field lines crossing each other's path. Like, oh, sorry, I'm not going to cross your path. Because if they intersect, then it means at that point you have two directions of the field. But field cannot have two directions. Either it is this way or it is that way. If field lines intersect, that means field is this way and this way. Is it this or is it this? You'll be confused. No, there cannot be confusion. So that's the reason why you should never cross the field lines. Another important thing is that the field lines are always going to indicate how strong the field is. Like over here, they are very closely spaced. If they are close, it's strong. If they are far, very weak field. So the density of the field lines tells you always the strength of the electric field. Is that clear? I hope this is understood. And yes, one last thing is that the field lines are always perpendicular to the surface of the charge. We'll come to more of that when we discuss conductors, okay? So don't worry about that perpendicularity now. We'll discuss more about it during conductors. So these are main things which you should definitely know. Also know one more thing. If the charge is strong, highly positive charge, more field lines will come out of it. If the charge is more negative, more field lines will get onto it, they will terminate onto it. So the strength of the charge decides how many field lines are going to come out or enter or end on it. Right? That's something which you should know. Let's see if you guys can figure this out. Hello Anish. I confuse, then start confusing from where you start. That's because you have to get into the habit of thinking, Susanta. That's all. So it happens. That's why always write down what you're thinking. Make a flow chart. What did you think? Okay, this, then this. So write down what you're thinking. Make a flow chart. Make a diagram. Often when you write things on a rough sheet, things become more clear. When you think mentally, you forget what did I think before. So it's better to always do things in the rough work. A and B points. Electric fields, where is it more or where is it less? It's always going to be open, Prem. It's only the magnetic field lines which are always closed. Yes, the magnetic field lines will be closed. You will never see that electric field line goes and comes back onto itself. Never, okay? So for static charges, you will not see electric field lines going and coming back at the same point. Yes, the answer is option A because here it's more dense. Here it is more rare. That means here the field is strong and here the field is basically weak. Definitely. So EA is stronger than the electric field at point B. Perfect. Now, electric field for a conductor, you will see there is an interesting thing which you should know, especially regards to conductors. So conductors, you will see always the charges lie on the periphery. Conductor means they are conducting. They can conduct electricity. So imagine you put positive charges onto a conductor. This positive will look at that positive, it will be like, I don't like you. He will say, I don't like you, I don't like you, I don't like you, I don't like you. Everybody like, I don't like you, I don't like you, I don't like you. So they will all go away from each other. They will all go away from each other. And in this process, what happens? The charges come onto the surface. So you will see that the charges are always on the surface of a conductor. Very, very crucial point. Never inside. That also means that electric field inside a conductor is always going to be zero. There is no field inside. There is never going to be field inside the solid part of a conductor. Keep this in mind. Luna, I'm extremely good. Yep. Yes. So even if you put electrons, it's the same story. If I put multiple electrons, if I put 10, 15 electrons, I'm like, I don't like you, I don't like you, I don't like you. All the electrons will go onto the periphery. So be it positive, be it negative, always the charges go on to the outermost periphery. So they will end up concentrating on the surface, never in the bulk or in the solid part of the conductor, always on the surface. So if I am a conductor, you will always see the charges on my skin and not in my organs or in my brain or inside my flesh. No, it's always going to be on the skin, remember that, if I were a conductor. Now, what happens to the outside thing? Outside, you will see electric field outside is always going to be perpendicular to the surface. That is one important characteristic of a conductor's electric field lines. It's always going to be perpendicular. Very, very important. No matter which part you take, be it a sphere, be it any random shape. Now, I can show you some geometries so that you get some idea. Imagine I take another geometry over here. So you will see the positive charges or negative charges will just line up like this somewhat. Okay. And the electric field lines probably will look something like this. Okay. It will look something like this. So observe. Everywhere it's going to be perpendicular. Okay. It's going to be perpendicular everywhere. Inside you're not going to see any kind of field. What if there was a cavity inside? Still you will not see any kind of field even inside the cavity. Imagine this is only the solid part. Only this much is the solid part of that particular conductor. Inside there is a cavity. There is a cavity inside. So I'll just put it over here. This is basically a cavity. And the remaining part is the conductor. You will see that the charges will only go over here. So the charges, even if it is positive or negative, does not matter. Right now I'm just showing positive. Doesn't matter, guys, whether it is negative or positive. Always the charges will come on the periphery, and you will see the field lines will only come from outside. That's it. There will be no field inside. There will be no field inside. So this is how the electric field lines will look like. Is that okay? Is this for charged conductors? Obviously, if there is no charge, then there is no field only. No charge, no field. No pain, no gain. No charge, no field. If there is charge, then it gets distributed. The moment you put charge, the moment you touch charge, zoop karke they will get distributed on the surface. Nothing will be there inside. They will all go outside. And you will see that the field lines come from outside. Nothing is there inside. Okay? I hope this is clear. There could be additional concepts where you put a charge inside the cavity. Well, yes, if you put a charge inside this particular cavity, another charge, let's say you put some positive charge example, then from this point to this point you will probably have some field lines like this. Only here, like this. In this part there will be no field. Please understand that. So in this part, electric field inside will be zero, but only in this part from this charge to this surface, because deliberately you put a charge in the cavity, that's why the field will come. If there was no charge here, this field will not be there. That's it. I hope this is clear. Godwin, I have already mentioned when I'm going to start 11th standard, okay? So first focus is obviously going to be on 12th standard. 11th will come later on. Everyone clear about this? Everyone clear about these concepts? So let's quickly revise. The field inside a conductor in the solid chunk is always going to be zero. Field will always remain outside if it is charged, and the charges also are always on the surface. Field is always going to be perpendicular to the surface of a conductor. All these are properties of a conductor. Keep this in mind. Just 1 second. So for hollow charge sphere outside, yes, we'll come to that. What will happen for hollow charge spheres, solid charge spheres, and everything. We're going to come to that. Okay, don't worry about it. Let's do some questions. Obviously, all kinds of geometries: solid sphere, hollow shell. How do you solve these questions? Don't worry, we are coming to that. First, let's come to properties of conductors, the questions on that, and then we'll proceed ahead. Okay, what do you think, guys, about this? There is a charged metallic solid sphere placed in a uniform field. The lines of force that will be following the path will be which of the following lines? Do you think the field line will come like this, end, start, or it will come like this, go around it and come like that, or it will pass through it as if the sphere is not there, or it will come like this, bend like that and come outside? I think only one of them is correct if this was a solid metallic sphere. Yes, it is option 4. Perfecto, guys. The reason for that is because first of all, the field is perpendicular, number 1. Number 2, the field inside should always be 0. In option 2 and 3, how is the field going inside the conductor? Wrong. So obviously 2 and 3 is wrong. 1, you can see the angle made is not perpendicular. It's obtuse or acute. So definitely it is not case 1 and definitely not 2 and 3 because it's passing through the conductor. It cannot pass and it should be perpendicular. Okay, so those are the properties of electric field lines. Now let's go to flux and Gauss law. We'll see geometries. We'll come to potential energy as well. I hope you guys are all excited about this. Okay, so what's flux? Flux means flow. Electric flux means flow of field lines. So flux in general means flow. So electric flux in general means flow of field. And this is directly proportional to the number of lines through a surface, number of lines cutting through a surface. An example would be this particular diagram. You can see a beautiful surface over here and you can see some field lines piercing through it. You can see some lines are piercing through it. If more lines are piercing through a surface, I would say it has good amount of electric flux. If no field lines pierce, it has no electric flux. Maybe we can look at certain examples to understand this situation better. Imagine a surface like this. Imagine a surface like this. Imagine a surface like this. And then also maybe imagine another surface like this. Okay. So I'm just going to show some field lines. Look at this. First case, the field lines are going like that. The second case, it comes like this. Just 1 second. Then another case goes like this, comes out, 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 goes like this, comes out. Okay. Another case, okay. Imagine just, goes like this and comes out. Okay. Now look at all these scenarios and think about how much flux or whether the flux will be more or less, as compared to the previous values. So if you look over here, this is the area. The field line is going over and below it. Nothing is going through it. It's not piercing through it. So I think here the electric flux should be 0. The symbol of flux is actually phi. The symbol phi is for electric flux. Here it is 0. Here I think there is some field lines piercing through it. Yes, flux is definitely there. It is definitely not 0. It is definitely not 0. Here also it is not 0. Here also the flux is not 0. But out of these three, if you try to compare the flux, think what will happen. If I assume this has flux phi 1 and this has flux phi 2, you can see here the field is more. More lines are piercing. So phi 2 will be definitely more than phi 1. Phi 2 will be more than phi 1 because field is more. Yes or no? Here, if you compare phi 1 and this, let's say for example phi 3, think logically, guys. Here the area is less, so fewer lines will pierce. If the area is more, you will take in other field lines also. If you reduce the area, you will miss certain field lines. So hence phi 3 will be less than phi 1. Yes or no, guys? Perfect. So that means it clearly tells you that the flux depends on how much strong the field is. It also depends on how much area you are talking about. It also depends whether the same area is tilted at an angle. Same area is tilted at an angle. So the angle, the field and the area together decide the flux. Now if you notice over here, I can define a new quantity called as the area vector. Area vector. So my area vector is going to be like this. Here also it's going to be like this. Here also it's going to be like this. But here it's going to be like this. Area vector is perpendicular to the surface. This is my area vector in all the cases. This is my area vector. Think about it. Here area vector is in the direction of the field. Area vector is in the direction of the field. So the angle between field and area is 0. Area and field is 0. Area vector, I have defined it. So cos of 0 is 1. Cos of 0 degrees is 1. Here angle between area vector and the field vector is 90 degrees. So cos 90 is 0. So that's why the flux is 0. I hope this is understood. So, but even if the area increases, lines per unit area. Lines per unit area is not flux, Shaku. Lines per unit area is something else only. You can define it as a new quantity. The total lines cutting through the area is proportional to the flux. It's not per unit area. That flux per unit area, that is the field strength and all of that. Okay, understood, guys? So that's why you will see that the flux formula, so if you don't like this symbol S, it's okay. Some books use S symbol, some books use A symbol. I like the symbol A. S, I don't like it so much. Okay, don't ask me why. So I can write it as electric field dot area vector, which is E A into cos theta. This is basically your dot product. This is basically your dot product. A is basically your area vector, guys. So you can see that over here as well. This is my area vector. Area vector is always perpendicular to the surface. Your electric field will be, let's say, this vector. Theta is nothing but the angle. Theta is nothing but the angle between the area vector and the field vector. So that is E A cos theta. Everyone? Cool? So if I ask you what is the unit of electric flux, what will the answer be? Field is nothing but Newton per Coulomb. Area is nothing but meter square. So the unit of flux will be Newton meter square per Coulomb. That's the unit of flux. Also keep this in mind, it is a scalar quantity because it's a result of a dot product. When you take the dot product of two numbers, two vectors, answer is always a scalar, like work. Force dot displacement, it's a scalar. So it's always going to be a scalar number. Okay, so I think this should be clear. Now, what about the flux of a point charge? And then slowly we are going to go towards other things as well. Okay, so when you look at a point charge like Q, then the electric flux totally coming out of it, the total flux coming out of a single positive charge is always the total flux from a point charge is always the charge by epsilon naught, or rather it is, you can say it is proportional to Q. It is proportional to Q because if more charge is there, more lines will come out of it. More lines will come out of it. So the total flux coming out of it is proportional to how much charge you place. More charge, more field lines. Less charge, less field lines. That constant of proportionality is basically epsilon naught, which is your, is nothing but your permittivity of free space. It's nothing but your permittivity of free space. Okay, everybody should know this standard thing. So this is the total flux through a closed surface, through a closed surface around a charge. That's very, very important. It does not matter what the shape or the size is. Always when you take a closed surface, you will see that the total flux will be Q by epsilon naught. One more thing I would like to point out over here. If you take a closed surface, imagine this is nothing but a surface. This is, let's say, a positive charge. Again, I take a negative charge. Again, this is a surface. If you see it's a positive charge, you will see field lines will come out of it. Field lines will come out of it. In such a case, the flux is basically positive. When it comes outside, the flux is positive. Whereas for a negative charge, you will see the field lines will end over here. So it comes inside. So here the flux is negative. This is the sign convention for flux. If it is coming out, it is positive. If it is going in, it is negative. I hope this is clear. Very good, Saran. Okay. No problem, Yash. And I understand that you guys are preparing for boards. But I really hope you guys watch it. And please do not think that I should only watch live classes. That is a very wrong notion which many students have. Sir, please conduct live class. I missed the class. Never ever think that, okay? Watch the classes as recorded. And you know, I'm always motivated. Even if few students watch, I will not think that, okay, I should not do this because it's going to be useful after a few days. I know that. Okay, coming up on your screen, surface is kept in the XZ plane in an electric field, 2I cap, 4J cap, 7K cap. How much flux comes out through this surface? Come on, let's see how many of you can do this. Let's see, come on guys. How much flux comes out of this surface? The surface is kept in the XZ plane. So basically, imagine if this is X, this is Y, and this is Z. So the surface is kept over here like this, XZ plane. This is your surface. So the area vector will be like this. Area vector will be like this. Area vector is basically 10J cap, guys. It is 10J cap. So if somebody asks you what is the flux, which is electric field dot area vector. So electric field is 2I plus 4J plus 7K dot area vector is basically 10J. How did I get 10J? By drawing, by visualizing. Without that, it will be little difficult unless you are very experienced. So you should understand, okay, it's an XZ plane. So the vector, area vector will be like this along the y-axis. So 10J cap. So obviously we know I does not go with J. Only J gets multiplied with J. Hence the final answer will be 4 into 10, which is 40. 4 into 10, which is 40. Perfecto, 40 units. Understood? So these kind of questions are very likely in your NEET examination or even in your boards. Moving on to another question coming up on your screen. The electric flux through the surface is largest or least or same in which of the figures? Charge Q, 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 Q. Okay. Shapes are different. Sizes are different. What do you think? Where do you think you will get the maximum flux or the least flux? Think about it. Come on, my dear students. What's the answer? Is it option D? Is it option A? Is it option B? Okay, Saran saying D. Everybody else? Aditya also saying D. Very good, guys. It is same for all the figures. Very nice. Reason being, if you have a positive charge, you will see the number of field lines coming out of it is just fixed. Doesn't matter where it cuts, but it will cut it. If there are 4 field lines coming out of it, the 4 field lines will cross that surface somewhere or the other. And what was flux? Flux was how many lines cut through the surface. If there are 4 lines here, 4 lines here, 4 lines here, 4 lines here. Yeah, it might not cut at the same place, but it is cutting now. Doesn't matter whether here or there. It's cutting. That is important. The same field lines, even if they shift, but number of lines is same, flux is same. And we are counting the total flux. So since we have seen that a total flux for a charge for any shape is Q divided by epsilon naught, Q is same. So obviously the flux must be also the same, independent of the shape or the sizes. Figure 1 is closed only. There is a misprint here. So I can see one small line because this is also an image or this is also an image, it has got cropped out. Okay, so I know some of you are like, sir, this is not closed. No, this is closed. Okay, so it's a printing mistake. You can see one small line. It's a cropped image, I think. So this is a closed image. Don't get scared. Okay, fine, bacha. But good observation, Yash. I appreciate your observation. Very good thinking. Like it. Okay. So now let's go to the next part, and that is potential. See, slowly we are building up on the concepts. We are more than halfway through, guys, in this chapter, and I'm very, very happy that you guys are here. And make sure that you're marking your presence by not just attending, but also participating in the discussions, writing down notes, and also subscribe to the channel, and make sure that you are also liking the video to show your attendance and to show your support. That's very, very important, guys. Okay, chalo, let's move on. Now, electric potential is a quantity which is a scalar. It tells you how much work you need to do to bring a charge from very, very far away to a point per unit charge. Imagine that, you know, there is some guy who does not like, for example, chocolates or sweets. So with great difficulty, you take one sweet box and you push it, take it from the sweet shop, bring it very close to him. It's very difficult. That guy does not like sweets. So you are doing some work, right? So how much work you need to do to bring a charge, unit charge, from a very far away, infinity, to a point per unit charge. That is your potential of that particular object or that point that you are talking about. Somebody likes sweets, so you don't have to do work. You will be doing negative work. You'll have to be like, wait, don't fly away from me. You'll be holding it. You'll be doing negative work, as the object will automatically get pulled if somebody likes sweets. Same way, if a positive charge is there, imagine if a positive charge is there, what will happen? To bring a unit positive charge, you will have to work against the repulsion. The work done will be positive. Hence, the work done per unit test charge, which is also going to be a small positive number, is also going to be positive in nature. Make sense? You will have to do work. Whereas if you take a negative charge, then what happens? In order to bring this same positive charge close by, you will not do work. In fact, you will be doing negative work. You will be doing negative work per unit positive charge. This W will be basically negative. Hence, the value of the potential will also be negative for a negative charge. So positive charge creates positive potential, negative charge creates negative potential. I hope this is understood. Great, amazing. What do you think is the unit of electric potential? Look at this over here. Potential unit. On the top, what do you have, guys? Joules. And at the bottom, you have coulombs. So hence, the unit will be joules per coulomb, and that unit is also called as volt. So 1 volt of potential is 1 joule of work done per coulomb of charge. If I do 1 joule of work in bringing 1 coulomb from a very far away point to that point, then the potential at that point is called as 1 volts, the same volts which you use in electricity. Exactly. Definitely, modern man, you can see this, no problems. Very nice. Now, what is the electric potential due to a point charge? I think, yes, maybe I'll just make it a point over here only. So if I take a point like this Q and I'm at a distance R from it, then the potential at that point is just given by 1 by 4 pi epsilon naught. Here you will have Q and here you just have R. No Q square, no R square. That's the important thing you should remember. There is no square of Q, there is no square of R. That's how simple the formula is due to a point charge. Now imagine there are multiple charges. Somebody will be like, sir, what if there are multiple charges? No problem. Imagine that there is a charge Q1 here, there is a charge Q2 over here. Imagine there is a charge Q3 over here. This charge will give some potential here. This charge will give some potential here. This charge will give some potential here. So my dear students, what is the total potential going to be? What is the net potential going to be? Potential due to 1, potential due to 2, potential due to 3. What will I do? I'll just add them, but be careful. Are they vectors? The potential is a scalar quantity. So don't put bar. You just have to add them. Don't worry. Cos theta, sin theta, no components. No components, just addition, because it's a scalar quantity. So you can just add them, just like you add charges. Whereas in field, you have to write E1 bar, E2 bar, E3 bar, see the directions. We solved some questions, right? Triangle, we saw what are the directions, and that's how we solved the question. So same thing over here, but do not put bar, just add them. Potential due to 1 is 5 volts, 6 volts, 7 volts, 5 plus 6 plus 7, 2 plus 1 minus 3. Whatever numbers are there, just add them like you normally add numbers. Okay, so that's potential. Now if there is potential, there is also potential difference. You might have heard this term, potentials difference. This child has this much potential. This child has this much potential. So what is the potential difference between these two kids? Okay, so you can take it whatever way you want to. So guys, the potential difference is just simply put the difference of the potential between 2 points. Okay, as simple as that. Imagine there is a charge, and at this point there is 5 volts. At this point there is 3 volts. So 5 and 3 difference is 2 volts. So that is basically your potential difference. Usual symbol is delta V, is final potential minus initial potential, or potential at point 2 minus potential at point 1, whatever you want to call it, in volts, of course. Now what is the use of potential difference, you might say? See, whenever something is at higher potential and something is at lower potential and you connect them, always the charges or the current will flow from high potential to the lower potential. So that is what you will see. The current always flows from high potential to low potential, and it does not continuously flow, guys. If it is flowing, fine, this guy's potential will reduce, this guy's potential will increase. High potential, low potential, current is flowing, so you will see this potential will decrease, this potential will increase till they equalize. So the current flows till equilibrium is achieved. Equilibrium in potential is achieved. That's very, very important. The moment the potentials are same, there is no need of any current. Current will not flow further. Keep this in mind. Let's do some questions. Two charges, 4 microcoulombs, are placed at the corners A and B of an equilateral triangle. What is the potential at point C? Everybody try to answer this. Come on, my dear students. Simple question on the formula. That's it. Come on. We're almost done. 70% of the portion, I think, for electrostatics and Gauss law. Few more things left. Let's see how many of you can do this question. If you draw a triangle, I think that will be better. Two charges of 4 microcoulomb. This is 4 microcoulomb. This is also 4 microcoulomb. Are placed on the corners A and B. The question is, what is the potential at point C? The side of the equilateral triangle is 0.2 meters. We all know that potential is a scalar number. So due to this and due to this, we need to find the net potential. So potential due to A and potential due to B. Potential due to A will be K, Q, both charges are Q, divided by R. Potential due to B will also be K, Q, divided by R. Q is same, 4. R is same, 0.2, 0.2. So this will just become 2KQ divided by R. So now it's just a matter of substitution. K value is 9 into 10 to the power 9, right? And the value of the charge is 4 micro, so 10 to the power minus 6. And here you have 0.2. Check what is the answer that you get. Check what is the answer that you get, my dear students. Yes, 36, perfecto. Yes, you can see 9 and this 4 and this 2 and this 2. This 2 and this 2 gets cancelled. 9 4s are 36. So it has to be 36 into something. So yes, option C. Yes, Ashrita, that's what you get. Perfect, perfect. Let's do one more question. How much work is done by the electric force in moving a charge from of 4 microcoulomb from infinity to a point? Electric potential is 10 to the power 4 volts. So imagine from infinity to a point, you have taken a charge of 4 microcoulomb and you have a potential of 10 to the power 4 volts. How much work do you think is done by the electric force? So if you look at the definition over here, potential is work done by the external force in bringing the charge from infinity to that point. Work done by the external force, not the electric force. Electric force might be working against the external force. Please keep that in mind. If I'm bringing a charge close, electric force is pushing me away, my force is pushing it towards. So they are opposite, keep that in mind. So over here also I need to bear that. Now we all know potential is work done by external force divided by the charge. So potential is also negative of work done by the electric force divided by the charge. So work done by the electric force is V into Q, but with a negative sign. Now over here, what is the potential? The potential is basically 10 to the power 4. What is the charge that you are moving? It's 4 microcoulomb. So 10 to the power minus 6. So this will become minus 4 into 10 to the power minus 2. That will be joules. So that brings me to option, obviously C. So negative answer. A lot of people miss that minus sign and mark answer A, but I'm so proud many of you thought the answer should be C. So why that negative sign is very important? Keep this in mind that, if my electric force is this way, then my external force is the opposite way. Hence the work done by electric force is negative of the work done by the external force. So in the definition of potential, it is always external. So if you want electric, put a minus sign. Then everything else is okay. Very nice, very nice. I hope, Cheetah, this is clear. Why that negative sign? Why that negative sign? It came from here, okay? This concept is very important. That's why you should know the definitions properly. Now, let's see the relationship between field and potential and then slowly go to dipoles and stuff like that. Okay. Now, we know that electric charges creates fields. So electric charges will also create potentials around it. And there will be certain points which have the same potential. So if I join all the points around a charge which has same potential, I will call it as an equipotential line, or if it is a surface, I'll call it equipotential surface. Like for example, if I take this charge, if I go here or here or here, all these points have the same distance from this charge. So hence, their potentials will be same. So if I join all these points, you can see a green color circle form. Those circles are equipotential surfaces or lines. If I go anywhere on this circle, potentials are same. On this circle, potentials are same. But this and this, potentials are not same. There is a potential difference. Now that you realize that, okay, this is the concept of equipotential lines and how the potential difference is created, you can probably write it down over here. There will be definitely some potential difference. There is potential difference between these two lines. You will see if you add the electric field lines onto it, superimpose, you will always see that the electric field lines always go from high voltage to low voltage, always. So if you see over here itself, you can notice that the electric field line will be going like this. This point, actually speaking, is at a higher potential. This is at a higher potential. This is at a lower potential. Because when you are close to the charge, the potential magnitude increases, here it decreases. So electric field is actually going from high voltage to low voltage. Not just that, you will also see that the electric field is always going to be perpendicular to the equipotential line. And not just true for a point charge. Any system of charges, like take this example. There's a positive and negative charge. Electric field comes from positive, goes to negative, comes from positive, goes to negative, comes from positive, goes to negative, every time. You will see these dotted lines are basically equipotential lines. Notice how at every point the electric field line is perpendicular to the equipotential line. That's important characteristic. Second characteristic, you will always see if electric field line is going from here to here, that means these potentials are higher, this is lower, 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 and so on and so forth. Always this is going to be true. Okay? Keep this in mind. So maybe I can just put it up over here itself. Just one second. So equipotential line or surface is always perpendicular to the field line. This is one important characteristic. The second important characteristic is if I have high potential and if I have low potential, then you will always see electric field line travels from high voltage towards that lower voltage. This is always going to be true. Okay, does electric field arise because of potential difference or because of electric potential difference is created? So there is no end to it, like you can call it either way. So electric field lines create the potential difference, or potential difference can also create electric field. They both happen simultaneously is something what you need to understand. It's not like I create a difference, that's why the field is there. It happens. The moment the potential difference is there, field is going to come. Okay, and same thing, the moment I create the field, you will see the potential difference will created by that particular field. Let's see if you guys can solve this. If A and B are two surfaces, minus 10 volts and 10 volts, what will happen if you place another point charge Q between A and B? What will happen if I place another charge Q between A and B? What do you think is the answer to this particular question? Come on, think about it. A and B are two equipotential surfaces. Let's mark those potentials. A's potential is minus 10 volts. B's potential is plus 10 volts. Oh, because of that, there will be electric field. How will the electric field be? From high to low, from high to low, from high to low, right? That is how the electric field lines will be, from high to low always. So the concept now is, if I place another positive charge here, where will it go? Obviously a positive charge will experience force in the direction of the electric field. Remember, force is the charge placed into the field. So whatever is the direction of the field is the direction of the force. So it will go towards A, guys. It will go towards A. Yes, it will move from B to A. From B to A. Yes, it's coming inside. That means option B. Correct, Ashrita. Yes, Dimple Divya. Perfecto. Okay, so this is the relationship between the field and the potential. Now, let's go to something called as potential energy. So this is also a very important concept, potential energy. Potential and potential energy. What is the difference? Why create two different things? Potential is the work done per unit charge in bringing it from infinity to that point, whereas energy is the actual work done in bringing those charges together at certain distance. It's not per unit charge, but it is the actual work done by the external force to bring the charges at certain separation. So the energy between two particles is just given by KQQ divided by R. KQQ divided by R. If you don't like this R1, 2 and all that, it's okay. It's just the distance between them. So if you now compare all the formulas that you have learned, force was KQQ divided by R square. Field was KQ by R square. Field KQ by R square. Potential or energy, they do not have R square. If it is potential, it is KQ by R. If it is energy, it is KQQ by R. So if you write down all the formulas, everything will be clear. Force, field, potential, energy. Force is KQQ by R square. Field is KQ by R square. Potential is KQ by R. Potential energy is KQQ by R. That's all. These are the main distinctions between the formulas. Energy is the actual work done in bringing the charges close. Obviously, it's a scalar quantity. And not just that, it is also very important to know that this quantity of energy, it's expressed in again joules. Okay, because it is at the end of the day energy itself. So any kind of energy, it's always going to be expressed in terms of joules. Now just imagine there are charges. There is one charge here, there are charges here. I take this charge and move it here. Right now, okay, if I probably mark it, these charges with this charge has some potential energy ui. Has some potential energy ui. Now the moment I move this charge here, you will see that the energy will change. Not just actually these charges, but even these charges with that charge. Notice how these charges with this charge has some potential energy ui. The moment I move this charge from here to here, then it has changed the configuration. It has changed the configuration of the system. So there is new potential energy uf. So what will happen? Energy will change. If I take a charge from one place to another, then the potential energy will change. So the change in the potential energy can be simply put calculated as the final minus the initial energy. Final potential energy minus the initial potential energy. But there is another way of calculating that. And the simple way is, just think guys, in the formula of potential energy, you just have one extra Q, right? If you hide this Q, doesn't it look like potential? Doesn't it look like potential? So KQ by R is potential into the charge. So if energy is potential into charge, the change in energy will be charge into potential difference. So this quantity over here is just your potential difference. Very, very important for solving problems also. You will see many times there are some energy conservation problems. Example, a charge accelerated through some kind of potential difference. What is the speed acquired by it? In solving these questions, the logic is very simple, guys. I'll tell you what you need to do. The potential energy change comes from the kinetic energy change, or vice versa. If a charge is accelerated through a potential difference, it will get some kinetic energy. That kinetic energy comes from the potential energy loss. The potential energy loss or change is charge into voltage difference. Use this formula. Kinetic energy change is just half mv square. So just solving this, you can easily find what is the speed of the particle. You would always see such kind of questions even in photons, photoelectric effect, or maybe some other chapter even like magnetism. So this is how you calculate the speed of the particle if you know the voltage difference through which it has been accelerated. So keep this in mind. So this problem, this concept comes in many places. Okay, chalo, let's see if you guys can solve this. When one electron is taken towards the other electron, then the electric potential energy of the system decreases, increases, remains unchanged, or becomes zero. Yes, potential is there due to every charge. Hello Gopika, thank you so much. Let's see, what do you guys think about this? When one electron is taken towards the other electron, then the electric potential energy of the system will. There is one electron, there is another electron. Right now, they are really far away. Now you bring them closer. What do you think will happen? If this was the potential energy, which was K, negative charge into negative charge divided by R. Negative into negative is positive. So K into positive, okay, divided by R. Here also, it is going to be, the new potential energy is going to be K into some positive number divided by that new R. But this new R distance is small, right? This is small, right? So what will happen? This energy will increase because it is in the denominator. This will be small, the ratio will increase, the energy will go up. So hence the answer will be increases. Perfect. Exactly. Option B is the correct answer. No, it's not decreases, it will be increases. So although it is negative, but negative into negative is a positive number. Be careful about it. So if it was positive negative, then it was a different story. Okay. Now, another important relationship which you should know between field and potential is that field is negative rate of change of potential with distance. Electric field is the negative gradient. Gradient means a rate of change. Okay, so if you don't understand this word, it is basically rate of change with respect to distance. That's what this word means. Of the potential, and it is the negative gradient. That means the negative rate of change. So always the field goes towards the lower potential. That's why this minus sign. Wherever the field goes, always the potential decreases. That's why that minus sign. And if the potentials change rapidly, it's dropping or changing rapidly, and the field is very strong. That's why there is a rapid change in the potential. That's what this expression says. An example for this question or this particular formula will be, if potential is basically x cube volts, then what is basically the electric field going to be? The way I solve the question is like this. The electric field will be minus d by dx of the voltage. In this case it is x cube, so it will be minus 3x square. That is the field. So if the field is asked at any coordinate, I'm just going to substitute that point and I'm going to get the answer. So in general, electric field will be minus 3x square I cap. So that's how you calculate the field. Yes, Gopika, I did. Okay, I hope this is clear. Everyone with me? Understood? Very nice. Let's solve some questions. If there are two plates at potentials minus 10 volts and 30 volts, separation 2 centimeter, then the field between them is going to be how much? Very common question, guys, for all of you in any kind of NEET exam or even in board exam. So what is the field between them? The moment you hear the words like field, potential, distance, immediately the formula that should come to your mind is E is minus dV by dx. But here I'm not interested in the negative sign, I'm only interested in the magnitude. So the magnitude of the field will be the change in the potential upon that distance. That's it. So what is the voltage difference? One is 30 and the other is minus 10. What is the separation? Separation is 2 centimeters. Okay, 30 minus minus will become plus, so it will be 40 divided by 2, and this will go as 10 to the power plus 2. So 40 by 2 is 20, so 20 into 10 to the power 2, so that's going to be 2000 volts. Wow, where is it? Yeah, 2000 volts per meter, my bad, because I have divided by distance. So 2000 volts per meter. That's the answer, option A. Yes, it is. Got it? Very good, Divya. Yeah, so these kind of questions are also very common. Okay, so I think I had already given the electric field lines properties with respect to the conductor. So electric field inside the conductor is 0. Electric field lines are always perpendicular. Electric field lines are never going to be inside a conductor. Charges are going to be outside. The surface and the volume of the conductor are always going to be at the same potential also, because if there is no field, think about it, if there is no field or there is no need of changing the potential. So all the points on the conductor are always going to be equipotential because there is no field inside the conductor. So that's another important point which you should probably add in the properties of conductor. So this one. Okay, everything else I have already mentioned, okay, before only. Let's do some questions. The electric field due to a conductor, charged one, just outside the conductor, just outside the electric field, just outside, is 0 and normal, 0 and parallel, parallel at every point and 0 inside, normal to the surface at point and 0 inside the conductor. Which one do you think is the correct answer? Okay, let's see how many of you can do this. Read the question carefully, draw the situation, only then you will get the correct answer, guys. Come on, figure this out. Figure this out, come on. Think. Option A, D, C. All right. I have a feeling it is not going to be D. It is going to be A, guys. Yes, it's not going to be D or C. Yep. So understand the question. First of all, let me draw the surface. This is the surface of a conductor. This is the surface. Let's say this is the inside of the conductor. Okay, this is the inside of a conductor. Is 0 and normal to the surface at every point inside the conductor? That's perfect. Electric field inside is always going to be 0 everywhere inside. That's perfectly correct. 0 and is parallel to the surface at every point inside the conductor? Wrong. There is no field only. How can it be parallel? Parallel to the surface at a point and 0 inside the conductor? No. How can it be parallel again? Normal to the surface at every point and 0. Everything is inside. Nothing is outside. If the word outside was used, then understand, then I would say at every point outside it is perpendicular and the field is going to be there. But the question everywhere is inside, guys. So because of this word inside, it should be 0. There is no sense of direction. Yes, Rajat, I do remember you. Perfecto. Going on to Gauss's law, which you have already seen just some time back, when I told you that the flux by a point charge is always charged by epsilon naught. So if I take only one charge and if I take a surface, then the net flux was the charge inside by epsilon naught. But what if there are multiple charges? One positive, negative, 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 positive, placed anywhere. Each charge will create its own flux. Each charge will create its own flux. So I have to basically add all the fluxes. Here also I have to add all the charges. Then I will get the law called as the Gauss's law. It says the total flux from a closed surface is charge inside by epsilon naught. And flux is nothing but electric field into area. Electric field into area. Now why this integration has come, you might ask? Reason is field is not same everywhere. Somewhere the field might be like this. Somewhere the field might be like this. Somewhere the field might be like this. Maybe at this point, if the field is here, through that small area that is there, which I will call it dA, the flux, small flux which will go, the small flux which will go, d phi will be E dot dA. E dot dA, small flux. So the total flux will be integration of that. The total integration of that will be the total flux through it. That's all. I hope this is clear. Okay. So tomorrow morning class at 10:30, bacha, boards class. So let's see if you guys can answer this. If the figure shows over here a distribution of charges, the flux of the field due to these charges through the surface S is how much? There is a charge Q here, and Q here. The surface S is this one. This is that surface S. So question is, what is the flux of the charges on that surface S? Come on, think about it. Question D option also says 0 inside the conductor, is it? But it also said normal. How can it be normal? There is no direction, normal at every point. Even though it says 0, how can some number be 0 and have a direction? Doesn't make sense. That's why that option is wrong, bacha. Okay, fine, Arya. Let's see if you guys can solve this question. Figure this bit out. Arya will be resuming 11th standard portions after, the 12th portions are over, not before that. Okay, cool. Come on, figure this out. Meanwhile, let me just... Okay, yep. So what do you think, guys, is the answer to this question? If you notice, in Gauss's law, it always says that the total charge enclosed, that means this should be always inside charges, not the outside charges. If you notice in this particular question, this is a charge which is outside, whereas these are the charges which are inside of it. So when I calculate the total flux through S, it is only going to be Q plus Q divided by epsilon naught. So 2Q by epsilon naught, not 3Q, guys. Yep, that's the answer. Option B, it's not going to be 0. This is Q and this is also Q. This is Q and this is Q. Yes, option B, very good. Not the outside charge. Always take the charges which are inside. You might be asking, sir, why do you not consider outside charges? The reason for that is simple. If you have a charge which is outside, right? Whatever flux enters in, exits out. Whatever enters in, exits out. So if there is some negative flux, there is equal amount of positive flux. Negative, positive. So that's the reason why the net contribution is always 0. Net contribution of that particular flux is always going to be 0 for a charge which is outside. But the moment it is inside, it contributes either positively or negatively depending on its sign. Okay. Moving on to another question coming up on your screen. 2 Coulomb charge is placed at the center of a cube. What is the flux through any one of the face? Gopika, it's usually changing. Now because it's board exam, so I'm keeping the board classes at the timing of the exactly same time as that of the board exam. So that's 10:30 around. So I'm going to take the board classes at the same time, but as soon as we come back to 11th standard, we are going to come back to the evening times. Okay? Yes. Okay, so let's see if you guys can solve this. Charge of 2 Coulomb is placed at the center of a cube. So if you take a cube like this, and you place a charge exactly at the center, what will happen? Some flux will come here, 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 some flux will go behind, some flux will go this side. So in all the 6 faces it will go. So what is the total flux of that entire cube? It is a flux because of a charge. How much it is? It is always going to be Q by epsilon naught. Q by epsilon naught. And each face has the same flux, whether it's on the top, bottom, front or back. There are 6 faces. So flux through each face into 6 is the total flux. So hence the flux through any one face is 1/6 of Q by epsilon naught. That should be the answer. Where is it? 1/6. What is electric flux? The charge given over here is basically 2 Coulomb. So I think I had to substitute that also. So the charge was 2. So if I substitute that, I will get this as 1/3 epsilon naught. So I cannot leave it in terms of variable. The charge was given to be 2. 1/3 epsilon naught is option A. Yes, perfect. Gopika, well, a daily class schedule, I'll do one thing. I always put it up on the Telegram channel. So usually in the mornings, I will try to put up the upcoming schedule. So for the next few days, whatever is the timetable, I'll put it up in the Telegram channel. Will that be better? I think that will be better. Yeah, I will be putting it up on the Telegram channel. Okay, now coming to the main part where you will see different geometries and their fields. So there are few geometries only for which you should know the field. Yep. So we are just going to come to that. So it is area vector quantity. Why do we use the vector symbol over the thing, David? That's because it's easier to operate it as a vector quantity, and it follows the principles and the rules of dot or the cross product. That's the reason why you treat it as a vector. Because area, if you take it, see, it's like a area, right? It's a surface. It's spread out. So if I want to combine it and put it in the form of dot or cross product, I need a line or a ray. So I drop a perpendicular. The moment I drop a perpendicular, it's unique. It's like a line and has a direction. So suddenly a surface becomes like an arrow mark. So that's why I represent it as a vector quantity. This is for NEET mainly. Okay. So let's see how many of you guys can remember the formulas. If you have a sheet, so due to the sheet, the electric field coming out of it will always be uniform and parallel. That's very important. If this is a charged sheet, the field lines always come out parallel. So this field is uniform field. Very, very important. That means no matter how far you go, the strength of the field remains the same. And what is important in such problems is how much is the charge per unit length? Per unit area. How much is the charge per unit area? So that is called as the area charge density, and through that only you write it as charge per unit area, which is Coulomb per meter square dimensionally. And then the electric field that comes out is sigma by 2 epsilon naught. This is a very important formula where sigma is the area charge density, the charge which is there on the surface per unit area. Very, very crucial. Sigma by 2 epsilon naught, and it is uniform on both sides. Okay, moving on to the next one. Okay, just coming to, okay, all this is already done. I don't want to waste time over here. Yes, so next important thing, electric field due to a ring. Electric field due to a ring, charged ring. You can see there is a ring of radius r. The total charge on this is Q. If you are on the axis at certain distance, what is the electric field? That formula is given by, look at this guys, very important again. So you will have 1/4 pi epsilon naught, or you can just call it Q. here you will have Q, which is the charge on the ring, and over here you will have X on the top, and here you will have R square plus X square whole raised to 3 by 2. Assuming this is X coordinate, here I have put it as Z, but you can make it X also, doesn't matter. X is the distance from the center. X is the distance from the center to the point. So that's also very important, is the distance on the axis, of the point from the center of the arc or that ring. Okay, X is that distance, R is the radius of the ring. R is basically the radius of the particular ring. Very, very crucial. Just like you have field, you also need to remember the formula for potential, guys. It's very similar. The only change is instead of X on the top, you do not get that X, okay? Here you just have R square plus X square whole raised to half. This is 3 by 2, right? This will just become half. That's the only change in the formula for potential at a point on the ring. Very important. Is that ring a conducting ring or an insulating ring? It doesn't matter because it's a thin ring. So even if it's a conductor, the surface and the bulk very close to each other. It's like a line charge. So it doesn't matter whether it's a conducting or a non-conducting ring, Ashrita. Okay. So both the formula is the same. The formulas differ only for spheres. We'll come to that as well. Then yes, let's come to this one. Electric field due to line charges. Electric field due to line charges, and then you have something called as the line charge density. Electric field per unit length. So lambda is basically electric charge per unit length. So how much charge is there per unit length? If I know in coulombs per meter, I can figure out what is the field around it using Gauss's law. You should know the formula for it. So if I have a line charge like this, lambda coulombs is there per unit meter. I am at certain distance from it. Then the electric field is just given by 1 by, here you will have 4 pi epsilon naught. Here you have 2 lambda divided by A. A is the distance from the line charge where you want to find the electric field. Very, very important thing. Okay? Great. Before one, what do you mean by before one? This one. This one was a normal non-conducting sheet. This is for non-conducting sheet. Okay, so you will see the field lines go on both sides. If it was a conductor, then you will see only outside the field will go, inside the field will not go. Okay, so I hope that is clear, Ashrita. This is for a non-conducting sheet alone. Okay, this is the formula for that. For conductors, it is sigma by epsilon naught, not 2 epsilon naught. Okay, now if this much is clear, I think this electric field due to infinite sheet I have already done. Electric field due to a conducting surface. See, when you have a non-conducting sheet, then you get that by 2 formula. But if it is a conducting surface, like this one, the electric field on a conductor, then it is no longer sigma by 2, it is just sigma by epsilon naught. Just think of it this way, guys. When you have a conductor, the electric field is only going on one side. It's only going on one side because inside the field is 0, right? Inside the field is 0. So the electric field is sigma by epsilon naught. There is only one number here. But the moment it is a sheet, the field goes on both sides. This side and this side. Half here, half here. That's why you will see in these cases the electric field value is sigma by epsilon naught, and you have this 2 over here. Half here, half there. That's the way to remember it for a non-conducting one. For a conducting one, it only goes on one side. That's why it is just sigma by epsilon naught. Okay, I hope this is clear. So ring done. Then even what do you say? Line charges done, and also we have done basically your sheets. So 3 geometries done. Now coming to basically conducting spheres and shells and all of that. Let me just come to that. Just 1 second. Let me make these slides ahead. Just 1 second. Just give me a minute. Yep. Okay. Now coming to the final part of geometries where you are going to see spheres and shells. Now whenever you have spheres and shells, usually understand that some of the things have very similar formulas. Okay, only few of them have different formulas. See, I'll tell you the difference. Observe this carefully now. If you take a conducting shell, or shell means it's basically hollow sphere. That means there is air inside of it. It's hollow, that's why it's called as a shell, like the shell of an egg. Or if you take a conducting solid sphere, or if you take, so this is a solid sphere, so I'm just making it solid, or if you take non-conducting or basically insulating shell, in all these three conditions, what you will notice is that the charges are only there on the periphery. On a conducting solid sphere also, the charges are going to be there on the periphery. There is nothing inside, the charges have no other place to stay but the periphery. So the distribution of the charges is same in all of them, hence the formulas are also same. The only difference comes when you have this one. This is conducting, right? So imagine insulating solid sphere. This is where all the difference comes in, guys. That's all. Everything else is the same. All these three have the same formula, let me tell you. If you go inside, right, then the answer for the field is 0 because there is no field. No field inside. The field lines are only outside. So the field outside will be K charge divided by the distance square. So this is when R is more than R. This is when R is less than R. That's how the formula works. If you look over here, what should be the formula? The formula for the electric field when you are inside will be different and outside will be the same. Reason being, in this case, the charges are not just on the periphery, but they are also distributed in the volume of that solid sphere. It's insulating. The charges can't move. In conductors, they always move. They go on the periphery. In this case, it's already on the periphery. Here, they are attached to that body. They cannot leave that position. That's why you will see they are distributed uniformly and they're just staying there. So hence, in this case, the field inside formula changes, but outside it just behaves like one single point charge, so there is no problem. So if I have to write down the field inside versus the field which is outside will be the same. It is KQ divided by R square. That's when R is more than R. But the moment R is less than R, it is KQ small r divided by R cube. That's the only change in the formula. I hope this is clear. So when you're outside, the entire charge can be assumed to be concentrated at a point here, center. So it behaves like a point charge, just like over there. Only difference is when it is inside. So I hope you now remember these things. Outside, inside, conducting, non-conducting, insulating, whatever, shell, solid sphere. You should know, are the charges going to be on outside or are they going to be distributed? If they are going to be outside, then use this. If they are going to be distributed, then use this. As simple as that. Yes, the graphs are also important for this. For example, even if you try to draw the graph for this, if you try to draw the graph for this, how will it look like? Obviously, it will be proportional to r, so it will increase. Then it is inversely proportional to r square, so it will go down like that. This is how the graph will look like for field. If you draw it for this guy, how will the field diagram look like? It is not there only, so it's 0. Suddenly it will climb up and again it will go down like this, proportional to r square. So this is how the graph of electric field will look like with respect to the distance from the center. Very, very crucial. Understood now? Understood everyone? Perfect? Excellent. Excellent. Great, great. Now, there is one more geometry for whom you should know the field. We have done rings, we have done sheets, we have done line charges, we have done solid spheres, hollow spheres, everything. That last geometry is basically none other than something called as dipoles. So what is the meaning of a dipole, guys? What is the meaning of dipole? Di means two, poles means polarities. So two polarities in equal amounts is called as a dipole. So imagine this, if I have a positive charge and if I have a negative charge separated by some distance L, if this is plus Q, if this is minus Q, that is basically a dipole. So two equal and opposite charges separated by some distance is called as a dipole. Now the strength of a dipole is denoted by a symbol P. P is the symbol for the dipole. So dipole moment, or just the dipole, whatever you want to call it, dipole or the dipole moment, is any one of the charge, so I can just call it dipole moment, is any one charge multiplied by the separation between them, so P, which is the symbol, is any one of the charge, Q or minus Q, one of them, magnitude only, into the separation, which is basically L. So this becomes the formula, and this is a vector quantity. Please remember that this is a vector quantity, and the unit will be coulombs into meter. Coulomb meter is the unit. It's not centimeter, it is coulomb into meter. And when I say it's a vector, what is the direction of the vector? It always goes from negative to the positive. Very, very crucial. So just look at this particular example. Imagine there is a plus 2q charge here, there is minus q charge here, minus q charge here. This system is actually a dipole. In fact, there are two dipoles. How? Look at this. I can convert this scenario as a positive charge here. This negative is as it is. This plus 2q, I split it into two q's, and this negative q as it is. Now you can clearly see that these two is a dipole, these two are a dipole. So obviously these two will create a dipole moment P1 over here, these two will create a dipole moment P2 over here. These two dipole moments are basically vector quantities. So if I take this dipole moment P1, this dipole moment P2, and if I add them vectorially, I will get their net dipole moment, which is the vector sum of P1 and P2. That's how you need to add them. Okay, so that's a dipole. Now these dipoles create a field around it. These dipoles basically, what do? They create a field around it. Observe how. Imagine this is positive charge. Imagine this is negative charge. This is positive, negative. How will the electric field lines look like? We all know. They always go from positive to negative. They'll go like this, correct? This is how the electric field lines will end up going. So many field lines are there. Great, I'm just showing few of them and also marking their directions. If I take any random point and I want to know what is the field at that point, say for example, this point separated from the center at a distance r, I want to know what is the value, of the electric field at this particular point. Now imagine I know how much is the angle made with the dipole moment Always remember the electric dipole moment goes from negative to positive, right? So the dipole moment is this way. I know at what position I am angular wise with respect to the dipole moment. Then the electric field at that particular point is given by 1 by 4 pi epsilon naught as it is. Here you are going to have P and you are going to have R cube. R is the distance from the center of the dipole, and here you will have root of 3 cos square theta plus 1. This is the field at any location. This is the field at any location around that dipole. You put the value of theta, you get the answer for the field. Not just that, you can also find the potential at that point. The potential at that point, believe me, is just 1 by 4 pi epsilon naught. Here, you just have P and you have cos theta divided by R square. P is the dipole moment, R is the distance from the center, theta is the angle made by the position with the dipole moment. You will get the potential at any point. Just to see certain special cases, in this case, let me tell you, this line which divides the dipole is always called as the equator. This is called as the equator, and this line which passes through the dipole is usually called as the axis. So if you take this point on the axis, here or here, the angle theta will be 0 or 180. So you will see the value of theta will be 0 degrees or 180 degrees. On the equator, the value of theta will be 90 or minus 90. So you can just put it as 90 degrees for now. That's the change. So accordingly, you can find the value of the field on the axis as well as on the equator. Just to calculate that for our sake, imagine if I want to calculate the field on the equator, it will be nothing but 1 by 4 pi epsilon naught. I will have P and I will also have R cube. Inside I will have 3 and I will have cos 90, guys. Cos 90 is basically 0. Cos 90 is 0, so plus 1. So this is just going to be 1 by 4 pi epsilon naught P divided by R cube. Because 3 into 0, 0, 0 plus 1, 1. 1's root is 1. Great, that's the field on the equator of a dipole. But if you calculate the field on the axis of a dipole, what is this going to be? 4 pi epsilon naught. Here you have P, here you have R cube, root of, here 3 cos 0. Cos 0 is 1, so plus 1. 3 plus 1 is 4, root of 4 is 2. So 1 by 4 pi epsilon naught 2p by R cube. You can see it is twice as that on the equator. So the field on the axis is strong as compared to that on the equator. You can see that very clearly. Everyone with me? Okay, so this is the field and potential due to a dipole. Very crucial, important for all of you. And the reverse is also very important, guys. What happens if you place a dipole inside a field? I don't know how many of you remember this, but let me just revise this also for all of you. If you take a dipole in a field, imagine this is your dipole and you place it in somebody else's electric field, you will see the dipole will turn, it will bend, it will experience a torque, twisting force. So there will be a torque on the dipole, and that torque is given by P E sine theta, where theta is the angle between them. So actually speaking, it is P cross E. That's the value of the torque that you get when you take a dipole and place it in somebody else's electric field. Why does the torque come, you might ask? Simple explanation. Because of this field, this positive charge will experience a force of charge into E over here. Because of the field, this negative charge experiences a pull this way. You can see this force is here, that force is there. These forces are anti-parallel but not on the same line, because of which they act like a couple and they produce a torque. In fact, if somebody calculates the net force on it, the answer will be 0 because QE here, QE there will cancel out. So the net force on a dipole is always 0, but the net torque is always present. Keep this in mind. Now, these formulas are only valid when the field over here is actually uniform. When it is actually uniform. When it is non-uniform, then this might not be 0 and this torque will not be P into E because the E value will keep changing. That's why in our syllabus, we only deal with uniform electric fields. Because the moment it is not uniform, here, everywhere the field will change. So what is the value of E that you are going to put? So hence, we are not going to discuss, or we don't have those kind of things where non-uniform fields are there and dipoles are there. Now, because there is a torque, there will be also energy associated. Just like when there is a force, there is potential energy associated. Same way, this particular dipole behaves like a spring and there is potential energy associated with it. Very important. Potential energy of a dipole in a field. Of a dipole in a uniform field. The answer for the potential energy comes out to be minus dipole moment into electric field. Just like you had sine theta here, you will have cos theta here. See, very easy to remember, torque is vector, so you will put sine because cross product is sine. Energy is a scalar, so you are going to use dot product, so you are going to put cos. That's better way of remembering it. Just keep this in mind, this negative sign is always going to be there. This negative sign is always going to be there in case of potential energy. So you can always write it as minus P vector dot E vector also. It's one and the same thing. Very, very crucial. Just to give you certain cases for this, imagine, let me just draw it. This is, okay. This is your electric field. In the first case, let's say dipole moment is like this. Second case, dipole moment is perpendicular. Third case, dipole moment is making 180 degrees. So here it is 0 degrees, here it is 90 degrees, here it is 180 degrees. Okay, with the electric field, of course. With the electric field, of course. So if I ask you in each of the case what is the energy and what is the torque, let's write it down. First, talking about torque. Torque is P sine theta. So it will be P E sine 0. Sine 0 is 0, so torque will be 0. So the torque value will be 0. You can see that. In case of 90 degrees, P is sine 90. P is sine 90 degrees. Sine 90 is 1. So it is just going to be P into E. In the third case, it's going to be P E sine 180. 180 sine is 0. So it's going to be 0 again. So no torque when dipole is either parallel or anti-parallel. But there will be maximum torque when the dipole is perpendicular to the field. If you talk about energy, things are a little bit different here. In the first case, energy will be minus P E cos 0. Cos 0 is 1. So hence, answer will be minus negative P, obviously. In the second case, it will be minus P E cos 90. Cos 90 is 0. So answer is going to be 0. Answer is going to be 0. So when torque is maximum, energy is 0. Crazy. And lastly, if you take the third case when it is 180, so it is minus P cos 180. Cos 180 is minus 1. Minus into minus is plus. So it is going to be plus P. So I'm not saying you should by heart this table. No. I want you to write it on your own, analyze it on your own. That's when you get a feel of these formulas. So you should know when energy is maximum, when energy is minimum, when torque is maximum, when torque is minimum. Not have to remember it, but if you know the formula, you will think, potential energy is cos theta, right? So cos 90 is 0, cos 0 is 1. Oh, torque is P sine theta. Sine is maximum when theta is 90 degrees, and theta is 0, torque is also going to be 0 because sine is 0. So that's how you're going to analyze the situations. Why the negative sign? It comes via derivation, Pooja, because you will see minus du by d theta is basically torque. Just like force was negative dv by dx, du by dx, or field was negative dv by dx, same way you will see torque is minus du by d theta. So that's the reason why you get that negative sign. Why should we take the direction of dipole moment opposite in chemistry and physics? Is it vice versa? No, it always goes from inside to the outside. That's it. It's from negative to the positive. I don't know why chemistry uses different rules. Just like in thermodynamics, there is no reason, but it's just historical reasons. It's just a tradition or a culture, I would say. Okay, so that's it from my side, guys. In today's lecture, we have done and touched upon all the important pointers and concepts of electrostatics and Gauss law today. So make sure you go through all the formulas and make sure that you revise through all these things as well. And I'll be giving you the notes in the Telegram channel as well. Okay, so make sure you join it. Thank you for liking and subscribing. Thank you so much. I'll be seeing you in the upcoming days for the board preparation. Bye bye. That's it from my side. Captain Shreyas signing off. Hasta la vista.